fields are generated as sum of kernels centered on data points. So you want this kernel of this vector field are saying how points are moving. So you want the kernel at data point to have some kind of smoothing effect, to say that if one point is moving, its neighbors would like to move the same way. And so you want to adapt them that say that if you are in the same class, you want to help each other. So you want the size of the kernel to be able to cover, say, a reasonable fraction, not a very large fraction, but a reasonable fraction of the neighbors of each point. So I took 5 percentile of the points that needs to be covered by the kernel, and I want this to be covered for at least 3/4 of the point. That's what little one means. Now, if you are in 2 different classes, you don't want something that happened in one class to influence too much something that happened in another class. So you have the opposite constraint, and so you can make up another way to estimate the data, and then you have the scale, and then you have two different values, and they may be contradictory, but at the end I found that taking the minimum of the 2 was what gave the best results. There is also, if I remember well, there was an affine transformation in the picture, and there was some penalty of it. I didn't work much on trying to optimize that number. I found that taking something like mu equals 10 was fine. Now, for the objective function, you have to fix sigma, and so the smaller sigma, the more weight there is on the more penalty there is on the error, and so if you take sigma, the smaller you take sigma, the smaller your training error is going to be. For the experiments I ran, I mean the sigma was, so the algorithm takes some time, so we have time to make sigma change during its evolution, and so sigma slowly decreases until the training error reaches some target value, and I picked, and it seemed to be okay, 0.5% in the experiment. So, and actually, for all these experiments except a couple, the training error at the end of the learning was 0. There's also a penalty here. This lambda is the penalty for, well, it's there. So for this was norm theta squared here. So the penalty for the logistic regression parameters. And I just just to lambda equals rho square. I mean, it should scale like rho square. And just thinking about it, it's a right order of scaling, and it's just scale. It is just to be exactly to be rho square, which was fine. Okay, here are some examples, and the first example is the one we saw before. So the 2 rings that magically separated so if you don't, so but this is also going to be repeated many times. So let's spend some time looking at this table. So this is a battery of classifiers that are applied to the data before estimating the diffeomorphism, and this is the same classifiers applied to the transform data at the end of the training algorithm. And the logistic regression here is what is optimized by the algorithm. So you may think as this cell here as the output of the algorithm, and the error associated with the algorithm. And this really is an easy problem if you look at, if you look at these 2 3-dimensional rings, any nonlinear method does well, and very well. 0. So, oh, by the way, this is a test error. I don't provide the training error. It's almost all the time 0. So, just telling you what they are, this is linear SVM, like logistic regression. They are very bad at finding a separation since the data is not linearly separable. And then support vector machine, random forest, k-nearest neighbors, and multi-layer perceptron with 1, 2, and 5 hidden layers. So these will be repeated for each experiment. Just some detail on the parameters. So for example, there are 100 trees with the random forest, and some details on the multi-layer perceptrons. By the way, I tried more than 5. That never helped. So I stopped at 5. And everything is implemented using scikit-learn. So all these classifiers were run using this package. Okay, so going back to the example of the 2 rings. Now you think of these 2 rings in 3D, and you imagine that you have extra dimension, which are just noise. So how does the algorithm perform in that setting? So if you increase the dimension, so again, the real data is in 3D, but you increase the dimension, you add noisy dimensions to reach 10 dimensions total, then you can see already the performance of the original classifier degrade, and of course also what happened at the end is also degrading compared to 0 already that we had in 3 dimensions. If you have more samples, you have 250 samples per class, then you start doing better, but if you start adding dimension, it's getting worse and worse. You can also compare the performances of the algorithm, and on that specific example, for example, it looks like this diffeomorphic approach is comparable to every other approach, and sometimes a little better.
So could you explain what you mean by adding dimensions? I mean,
so this is adding dimensions in the original data. So it's very simple way to represent what happens in practice. In practice, you have some data, and you observe a lot of variables, and some are relevant, some are not relevant. So here I'm assuming that 3 variables are relevant, and the other 7 or 17 are just noise. And by the way, I make things harder and apply a random rotation to the data, because if it were all happening in the first 3 dimensions, it's too easy to solve. So there's a random rotation, so you don't know which 3-dimensional space is the data is. So this is this example. So now we're looking at, I think it's 10-dimensional problem visualized in 3 dimensions. So you can understand that there's not much remaining visible. But these are the 3 dimensions that are the best for the final classifier. So at the end, that after transformation, that gives you that. And I like it because you see the torus here. Well, there's no video with that. And here's another example. Again, if you know how the data is built, it's a very simple classification rule. But it's just an XOR in which, did you say XOR or XOR?
XOR.
XOR? Okay. So it's an XOR that is in 50 dimensions. So you have 50 dimensions. You pick 2 variables in that dimensions, not the same every time. And one of them is 1 or -1. I mean, they're both 1 or -1. If they are the same, so either both of them are 1 or both of them -1, it's class 0. If they are different, it's class 1. So it's very simple, and you just compute the sum of your data, and you have the classification. It's either 0 or 1 or 2 or -2. So it should be easy, but if you are in 50 dimensions and run this problem, well, most classifiers fail. Surprisingly, this diffeomorphic approach worked, and that it's not the rule. It's not always a big difference like that. But in that specific example, it worked better. And when you starting with 100 samples per class, when you increase the number of samples per class, then neural networks catch also the classification. And I'm not claiming that this is the absolute best that each classifier does. I mean, I took these parameters if you work specifically with a multi-layer perceptron, you may find a better way to address, to solve this problem. It's a very simple problem after all, but this is just using the parameters that I described. It's nice also because this is, the transformation, same thing as before, so projected in 3 dimensions, seems to be capturing, kind of natural, the fact that there are 3 connected components in the classification rule. The class where the 2 objects are the same or can either be both 1s or both 2, and this is what you see with these 2 regions here, and that would be the class in which you have 1 and -1. And there may be a video also, just to see how things are.
So I have sort of a naive question, which is, could you have predicted this without data, like analytically, what the resulting diffeomorphism should look like?
I mean, I can pretty easily make a rule. It's easier to generate, but yeah, I mean, you can. I mean, what? I don't know what the optimal diffeomorphism in terms of this cost function would look like, but what one possible diffeomorphism would look like would be very easy in this example. Same as one hidden layer perceptron would work. And a very easy way to generate that. So it is just whether without input, it's high-dimensional space, the classifier can get the answer. All the examples I'm going to show are going to be very simple in that sense. Well, not all, but for example, this one is more fun. Okay, I don't think you want to read the detail. It's kind of a way to generate some function that's a sign of this, of the sign of a sum of radial basis functions. This is how it looks like in 2D. It was this nice pattern, so I just decided. And can you see it? So okay, you have some green, you have some red, you have a red island here.
It's a 7.
It's kind of a. It's what?
No, it's a standard. There's a standard image where you're supposed to see like a number, right? Like a 7.
Yeah, I must know you. The thing, yeah, yeah. The thing when you tell you you're colorblind. Yeah. Okay. Anyway, this is what ran, and so here the results are as follows, and you can see that it's really tough when you have even in dimension 2. Just to estimate them. When you think of it, there are in this image 2,000 circles. I mean, some are on top of each other, but to get this density, you need a lot of circles or spheres here. So think of having 100 there and trying to extrapolate the shape of the region. It's not surprising that even in dimension 2, it's challenging. So with 100 samples, you get not too bad, but error rates, which are the best one, should be around 14%. If you increase the number of examples, everything gets better, and you get, so with 500 samples per class, you get something which is not too bad in 2 dimensions. In 3 dimensions, things become, so now you have to think, I mean, now it's really 3 dimensions, so you have to think as the same pattern, but instead of applying to something within a disk, it's something within a sphere. So you have these complicated regions, but they are in 3D. And there, okay, the classification rates mostly increase. Not always, of course, it's random samples, so things can have some variation. In 5 dimensions, it becomes very difficult. So these are the best rates that I observed. In 5 dimensions, this is before training, this is after training. This is the kind of thing that happens. So now, actually 6 dimensions, because as always there is one other dimension, and this is the data. This is the transformation of the type. But they're all the same. Okay. move quickly. I have a few more examples. Maybe I won't tell you everything. That is, again, a very simple, well, that one is, this is a very simple problem. You are, imagine a circle, and you have all zeros, except one segment, which has ones. So the circle has 100 points. The segment can be anywhere on the circle, but the length of the segment is 10 in class 1 and 11 in class 2. Again, trivial problem to solve. You just compute the sum of your data. If it's 11, you are in class 2. If it's 10, it's in class 1. I added a little bit of noise to make things slightly more complicated, but it's what happens. So it should be easy. And classify. I mean, it's really challenging to learn this rule. You can see that for this particular example, the best performance are obtained by neural networks. And diffeomorphic method, okay, improves a little bit over the others for improve a little bit compared to those which are not neural networks, but do not catch correctly the rule, probably not before you get 1,000 training samples. Yeah, I like that one. Just this is how the data looks like. So when you don't know how it is generated, I mean, can you imagine? I mean, this is all over the place. The classes are just very close. By the way, that what makes this problem challenging is that if you think about it, if you take one class, the data point which is the closest to it is in the other class, because the distance between the closest point in one class to one in the other class is one difference. If you are in the same class, the other data point is going to be shifted, the distance is going to be 2. So the classes are really on top of each other. And if you don't know what is the correct separation hyperplane to distinguish between the classes, it's very difficult to find it. So this is how the data looks like when you project it in 3 dimensions. This is how it looks like after learning. And it's really created this kind of very thin difference between the point, but after all, for a linear classifier, they're the same. Just to look at the video. Okay, another example that I tried. You have, just quickly, you have a curve now. A simple curve like that, and you have another one that let's make it a little different, like that. They are not very different. The definition of the curve is given here, and what you observe is small data point. So this is one sample. This is another sample. So some intervals in the curve. So that's what the data tells you when you have to classify the classes, and so. Here again, here are the results that I get with this method, and maybe I should stop because there are many of them. I tried MList, small MList data set, so 100 samples per class, and with instead, so the MList image of 28 by 28 was much faster for me to run with 14 by 13, and it turns out that all these classifiers did the same, whether it was 13 by 13 or 48 by 48 with this amount of data. And, well, you don't see much difference. I mean, they kind of, I mean, not a big difference. Except SVM, I don't know why SVM is so bad.
Is that digit recognition?
Digit recognition. Oh, yeah, sorry. And this is a digit recognition data set. And each image is 1 digit, and you have 10 classes.
So how do you subsample to 14? They were 28 by 28.
Yeah, you just
crop?
Yeah. No, not crop. Just take the average.
I see.
So each each pixel is the average of 4 pixels. A few remarks before concluding. So first, you can see that the kernel scale is important. So this is rho 0 is the scale that I selected, and you can see that it matters. Although around rho 0, you can also see that it's not that bad, except for this example. So XOR with 100 training sample, there is a huge variation, and this is with the rho 0 that I use. So you would do much better with a larger scale. The time discretization is as expected. You kind of converge to the limit classification rate. It's natural because the whole thing is a discretization of an infinite dimensional problem. So there are a few surprises, like where is it? Here, you get better with small discretization. And of course, the number of time discretization, you may want to think about it as a number of layers in a network. But in that setting, it's very different. The motivation is having an infinite number of layers. That's what we start from. Yes.
But here it was the time discrete problem was just earlier scheme, or it was
an earlier scheme. All right, that's it. Well, I still have one slide after that. This is just to conclude that this is really preliminary. I guess it's at best promising. The computation time is order of magnitude longer than any other method. So there is a lot of work to be done just to be able to scale up. I think we have a few ideas that can work. We being me a little bit, and Michelle Laure, who is starting to work on just applying this to regression problem instead of classification, just so that she can. This is not a big change, moving from regression to classification, at least conceptually, but these images show that you can actually, at least for this small dimensional image, work out a prediction by nonlinear regression using this approach. And that's it.
time for question.
Laura, do you know about t-SNE?
t-SNE? It's a cluster, it's a visualization method for...
So I wonder, right, but it can be used for this kind of thing. I wonder if there's a relation. The examples you gave, I would have thought, I just thought those are kind of ones that t-SNE seems to work.
I would not be surprised that other dimension reduction method, not all of them. For example, those for which the distance is misleading in terms of class, that may not work. But many of them, like the XOR, that could work. Yes.
Okay.
Any suggestion as to how to choose those kernels for these different tasks?
So I always use the same kernel. It's pattern kernel, and it's a good one because it corresponds to choosing V to be a subordinate space of some order. So it's not. It's very interpretable, and that's one thing. Except the result, the classification rate, whatever they mean, the fact that you really know what you're doing. At least if, like me, you spent a few years on the subject, is really good. This method is a basic statistical non-parametric method with some penalty on the transformation. It's clear how it is designed, and maybe there are some hope of getting also some results in terms of generalization error in statistics and accuracy of prediction based on this framework is probably easier than based on neural networks.
Yeah, just one name question. Is the structure of the underlying manifold of the dataset not before you training it?
No, it's just get. I mean, you just have the training data and you don't know anything.
Then do you have always necessary to go through all the dimensions? I mean, you could just go the very good result and just use a submanifold of this underlying manifold. We still need to go through all the dimensions.
So you don't. I mean, for most of the example, you don't know which dimensions to take. You have some magic space in which you can project.
Yeah.
And if you know how the data is generated, you know it. But if you don't, you cannot guess it. I mean, not by looking at the data first. But for example, using manifold learning method, you may be able to. But
diffeomorphisms here were considered as solutions of differential equations, right?
yes.
Are there obvious diffeomorphisms that class misses?
Yeah.
Are all the diffeomorphisms contained in the class as? I mean, you might be missing on some.
It's a class of diffeomorphism, but very big, so it's more than enough. For example, if you use the Sobolev kernel, the one I used, all diffeomorphisms that are of Sobolev types are
included.
That's been said, and correct.
Collective of identity. The penalty from identity to file, in a sense, it's making the prior that the original configuration is not too bad, no? Because I mean you're prevented from moving too far away.
Yeah, but I'm cheating a lot by introducing a mathematical transformation. The family of transformation that you have by using this kind of vector field, there is a penalty of the affine transformation, so there are also distance to the identity that creates a much larger variety of transformation.
Because if you are making this penalty very small, for example, or even close to zero, what would happen? Because you still numerically get something very
You
close
would
to
overfit. I mean, or not. This is what is here. So I mean, it's not very close to zero. Or no. Sorry, no, I don't have. I'm trying. So I'm putting the penalty as far as I can. So as close to zero as I can to get an almost exact prediction on the training data. So that's what will happen. The smaller this penalty, the more easier it's going to be to fit each point individually. Certainly, at some point, it will overfit. I think the intuition becomes really the usual intuition in statistics when you have a regularization parameter.
Could this method be used to uncertain values? I mean, uncertain values like so you use the data on, given values, a set of given values, could that be used like a Gaussian process or something distributions?
I'm not sure what would be the problem. What is your
if the value is uncertain, randomized data, would that still work?
noisy data?
Yes.
Yeah. Some of them were noisy data. I tried with mixture of Gaussians also, kind of thing that works comparably. Is there food in the 301?
That's how you